So let's take a look at an example of computing a surface integral over a vector field. So we want to find the surface integral, and again, this is our notation, and it might be confusing notation, over a surface S with a function f, and in this case, our vector field function is going to be given by y, comma, negative x, comma, z squared. And our surface in this case is already parameterized for us, and the parameterization is going to be given by u cosine v, u sine v, v. And our bounds in this case, u is going from 0 to 1, and v is going from 0 to pi over 2. This is a new surface. This is one that we haven't seen before. This is one that I wouldn't expect you to come up with yourself, but I think it's nice to illustrate what's going on here. That we do see that there's some sort of circular motion going on in the xy plane. We see that our radius is the coefficient on the outside, and that's going from 0 to 1. And our v values are the angles. So we see that in the xy plane, our radius is going from 0 to 1, and it's swinging out in sort of a circular motion. The difference is our z variable is the angle, which means that as our theta, so as our v progresses, we're sweeping in an angle, and we're also gaining vertically in height. So it means that this is actually something called a helicoid. Maybe that's too much information and you don't really care, and that's fine. But when v equals 0, we're along this length, and as v increases, it's like a sort of a staircase, that as our radius goes from 0 to 1, and we're sweeping out along this spiral staircase until we get all the way to pi over 2, which is exactly in the negative direction. So this is a z value of pi over 2. Anyway, so this is the surface that we're looking at, and we're looking at a vector field that looks like this. So let's go ahead and compute this double integral. What are our steps? We have to come up with a normal vector. So the first thing that I'm going to do is I'm going to compute my t sub u and my t sub v, which are my partial derivatives of my phi function, phi sub u. I'm going to move down a little bit. I think I'm going to run out of room. So t sub u equals phi sub u, which in this case, my partial derivative with respect to u, I'm treating v as a constant, and so cosine of v becomes my coefficient, and then sine of v also becomes my coefficient, and then the derivative of v with respect to u is just 0. My unit tangent with respect to v is going to be the partial derivative of my phi function with respect to v, which in this case, the derivative of cosine is negative sine. So I end up with negative u sine v, and then u cosine v, and the derivative of v is 1. Sorry, this should be a v down here. So to compute the normal vector, I'm going to take the cross product of these two things, tu crossed with tv, which is the determinant of the 3 by 3 matrix with cosine of v, sine v 0 in the second row, and negative u sine v, u cosine v 1 in the second row. And when I take the determinant, I see that I get I times sine of v. So sine of v times I for the first component, minus the determinant of the 2 by 2 given by cosine of v minus 0. So this is cosine of v j. Right? This times this minus this times this. And then finally for my k component, I get cosine of v times u cosine of v, which is u cosine squared of v, minus a negative u sine squared of v. So what does this simplify into? It looks like this becomes sine of v, negative cosine of v, and I can factor out this u and get just cosine squared v plus sine squared v, which is 1. So I just get u in the final component. So now that I found my normal vector, that was step 1. This is my normal vector. The next step, and I'm going to leave that down at the bottom, step 2, I'm going to look at what is T of phi. No, F of phi. Step 2, what is F of phi of uv? So I'm going to take my phi function, my parameterization, and plug it into my f function. And what do I get? My first component of the f function is y, so let's plug in what y is here, and in this case y is equal to u sine of v. My next component is negative x, so I'm going to look at my second component and plug in negative u cosine of v. And then my final component is z squared, and in this case z is equal to v, so I end up with v squared. So this is my f of phi of uv, and I'm able to write out my integral. So in this case, we're integrating as u goes from, the bounds on u are going from 0 to 1. My v values are going from 0 to pi over 2. And my f of phi of uv dotted with n, in this case, is given by f of phi of uv is written right here. Oh dear, I'm totally out of room. It's going to be, I'll just erase this because we know this. F of phi of uv is given by this vector, which is u sine of v, comma negative u cosine of v, comma v squared. And I'm going to dot that with the normal vector, which we found down here. Sine of v, negative cosine of v, u, dv du. Let's take this dot product, and recall that dot products, I multiply the first components, and in this case, I get u sine squared of v. I multiply the second components, the negatives cancel with one another, and I get plus u cosine squared of v. And then I multiply the third components, and I get plus v squared u. This is all a double integral dv du. Now I'm ready to, I'm going to do some tricky algebra and see that u is the same coefficient on each of these. I factor out the u, sine squared plus cosine squared is 1. So this actually just simplifies into being u plus v squared u dv du, which isn't that bad at all to integrate. So first I'm going to integrate, let's see, v equals 0 to pi over 2. So I integrate with respect to v first, treating u as a constant. I end up with, not forgetting my integral on the outside, I get uv, treating u as a constant, plus 1/3 v cubed u, evaluated from v equals 0 to pi over 2. What is that? Plugging in pi over 2 for each of these, I end up with u times pi over 2 plus pi over 2 times pi over 2 cubed, which is pi cubed over 8, and 8 times 3 is 24. So that was just my mental math of plugging in pi over 2 in for v cubed. And I get 24 over pi cubed, because there's the 1/3 there, times u du. I do my final integration step, integrating with respect to u. This is just a single variable integral. I get 1/2 u squared times pi over 2 plus pi over 3, 24ths pi over 3 times 1/2 u squared. And when u equals 1, I evaluate this from u equals 0 to 1. When u equals 0, all of this turns into 0. But when u equals 1, dun, 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 I get pi over 4 plus pi to the third divided by 48. And that's my answer. So no one said that this was pretty, but it's really not that computationally difficult. What were the steps that I did? I had this vector field. I had this parameterization of a surface. I computed the normal vector to this surface by computing TU and TV, and then taking the cross product to get my normal vector. That was step 1. Step 2 is still written here. I evaluated my vector valued function along this surface by plugging in the x, y components into this, and I got this vector. And then the final step, I take the dot product of f of phi with the normal vector and integrate.